This is a quick video, I hope, about intermolecular forces and bonding. Let's just start with, in general, intermolecular forces. This is a presentation that I got from another teacher, another website. It'll basically cover the same things. An intermolecular force is the force between different molecules, whereas intramolecular force is within, like I always use the example of intramurals, like games within the school. Intercollegiate is between separate schools. So anyways, intermolecular, and you have it between different molecules. Now, if those molecules are ions, you have ionic forces. Then you can have covalent molecules having bonds, and you're then going to have the intermolecular force of covalent bonds. Now, within that, there can be several different types of covalent. There's hydrogen bonds, which are pretty strong. Dipole-dipole bonds, which are that's between two covalent or two. You start looking at polar types of molecules, polar covalent molecules, and London dispersion is non-polar covalent molecules. So you can see that the non-polar London dispersion are very weak. Now, covalent bonds themselves, that's more of a, not really inter, but more intramolecular. I don't know why they have inter there. Very strong. But anyways, hydrogen bonds are probably the next strongest within the intermolecular forces after you're dealing with ionic as well. So you can see as they kind of get together that these shaded areas are the electron clouds and the distribution of those charges. It's very equal if you have two hydrogen bonds, so two hydrogen atoms. So you have the same atom, it's equal. That gives you that non-polar. But once you get a polar molecule, you can see that you start to get a partial positive on one end where the electron distribution is not there. And then you have a partial positive on the other end. And that's all based on that electronegativity. Okay, so intermolecular forces are based a lot on electronegativity. So here we go. A partial negative on the more electronegative element, a partial positive on the less electronegative element. Same thing here. All right, so let's start to look deeper into these bonds. London dispersion, you get them with all polar and non-polar bonds. So if you were asked, hey, you've got this polar molecule, what forces are there? You'd say, well, there's dipole-dipole. And there's also London dispersion. There's almost always London dispersion. You probably wouldn't talk about it with ionic so much, but definitely you would talk about it with the polar and non-polar molecules. Definitely the weakest. And it's usually because London dispersion is between molecules that have equal distribution all the way around the outside. So here's helium atoms, but really it could be a molecule like CH4 that's the same terminal atom all the way around the molecule. So that's the symmetrical distribution gives you the London dispersion forces. The unsymmetrical is going to give you probably more of the dipole-dipole. Now, within London dispersion, you can also have induced dipole. And that's kind of what we're talking about here. If they push into each other, then you get a partial negative attracted to a partial positive, like the clouds can push in each other. It happens in the larger molecules, not so much in the smaller molecules, but that's how you get larger molecules have stronger intermolecular forces, even though they're nonpolar, because they can induce the dipole, like those big fluffy marshmallows or Nerf balls that push in each other and create a sticky situation, sticky clouds. Dipole-dipole, it's you have the partial positive and partial negative, and they're pretty strong, and they're attracting each other. And so, whereas your non-polar molecules are London dispersion, most of them are gases. You're looking at helium, you're looking at methane, you're looking at carbon dioxide. With the dipole-dipole, you're looking at things like, well, water experiences that. We'll talk more about that in a second. You're looking at ammonia, you're looking at even your alcohols. These are all dipole-dipole bonds, and you get them to be liquids. Here's some examples with hydrochloric acid. Again, hydrochloric acids, you see that a lot in water too, but hydrochloric acid dissolved in water, and then you can have ion dipole bonds as well. So anyways, it's talking about the partial negatives and partial positives, and the dipole forces of attraction between positives and negatives on different molecules. It's not between the positive and negative on the same molecule, the partial negative and positive on different molecules. So here you can see this polar molecules if it's a solid, it's kind of locked into place. It's almost like a crystal because it's a regular repeating pattern. The liquid, they're still kind of rolling over one another, and they're kind of loosely held together. Again, they're going to be moving, but they're going to be exchanging that. The molecules themselves are going to be moving a little bit and exchanging one bond for another bond because they're always going to be attracted to a more positive or a more negative side. The hydrogen bonds are the strongest. And if you remember, with a hydrogen bond, it can only happen with nitrogen, oxygen, and fluorine. So water, ammonia, if you had hydrofluoric acid, it's got an F in it as well. Those are the only times when you have the nitrogen from one attracted to hydrogen on another. You have the oxygen on one attracted to hydrogen on another, different molecules. So very strong bonds. And they sort of do it, if you look at a graph of boiling points, melting points, things like that, you're going to see that difference. And we're going to show you that in a little bit. Here are the lone pairs. The lone pairs are what are very partial negative, and they're attracted to the partial positive, usually of the hydrogens. So you can see that graph. I think these pictures are very good in showing you where the regions of partial negatives are because of the lone pairs and how they get attracted to the partial positives. Here's a water, and we've kind of already talked about this, so we're going to skip over this. Now, they're talking about how hydrogen bonding works. And you look at this, here is the boiling point of hydrides. And so these are the different molecules that have hydrogen bonded to them, CH4. It has a very low boiling point. It becomes a gas very easily. So it's, negative 200 Celsius, or I'm sorry, negative 150, 160 Celsius. Lead hydride is almost starting to boil at almost 0 degrees Celsius. So the reason it's so much higher is because each central atom gets larger and larger as you move over here. And so, as I just said, the larger the molecule, it's got this large electron cloud that's kind of sticky, and it will promote this induced dipole and get it to have stronger bonds. Stronger bonds, when we talk about boiling point, melting point, viscosity, surface tension, etc., vapor pressure, it's all about those bonds, and the stronger the bond, the higher the boiling point. Okay, so the higher the melting point. And so large molecules, large nonpolar molecules, stronger bonds, induced dipole, and so you're gonna have higher boiling points. Now, we look at it here, and this is the same kind of thing where you have hydrides that, as you move up, you can see that the molecule moves up because the central molecule is getting larger and larger. However, you look over here, and it's weird because these have really high boiling points relative to the rest of their group when they're small, and water being super high. And that's because of hydrogen bonding, fluorine, oxygen, and nitrogen. All right, so there is some clear evidence. And you talk about the H bonding increasing the boiling point because the hydrogen bond is stronger. It doesn't happen with all things, just those three elements as they bond with hydrogen on a different molecule. And this is interesting because water is that very rare substance that actually the volume increases when it freezes. And you can see that when it's a liquid, they're rolling over one another. The little green dots are those hydrogen bonds. But now is a solid, it locked into place in these little hexagonal crystals, and there's lots of open space. And so it's kind of an interesting, it's an interesting thing that does that. And I don't really, to be honest with you, I don't know all the details of it, but it's something to remember. I know that a lot of people got tricked on one of our tests because volume increases when there's when the temperature decreases, when you freeze water. And so I just wanted you guys to see that and remember it. And so, you get to see, here's the overview of the whole thing. We talked about the weakest being London dispersion forces, and you get some induced dipoles with larger molecules. A great example of that would be in the halogens. You go from gases, you're talking about Brinkelhoff diatomic molecules. Fluorine and chlorine are gases. Bromine is a liquid. Iodine is a solid because you got larger and larger, and the bonds became stronger and stronger. That's the induced dipoles. Then you have dipole-dipole forces. So you've got hydrogen disulfide, you've got some methyl chloride, something like that, that does not really include nitrogen, oxygen, or fluorine. They're polar molecules, as you can see. They would have some lone pairs or an asymmetrical molecule. Then you go into hydrogen bonding. It's the next one up. And you're looking at examples like water, ammonium, and hydrogen fluoride or hydrofluoric acid, where it uses those. So definitely pretty strong. The next one up is ion dipole, which makes sense because if ionic is so much stronger as an intermolecular force than dipole, that an ion dipole in the middle would be pretty strong. So if you put a salt in water, the salt is actually going to the salt's going to create that ion dipole bonding, and it's going to increase the boiling point of water considerably because of the ion dipole bonding. We don't get into it. We'll get into it later. It's how you can, why they put salt on roads. It's called colligative properties, but in this particular case, it's also talking about the ion dipole forces. And finally, ionic bonding. So there you have your salts, and that's how that works. Okay. There's some pictures: ion dipole, ion-induced dipole, dipole-induced dipole, dispersion. Basically, it's kind of what we've already talked about. But what I'd like to do is, let's see if I can do this. Oh, I know. I have another video, or not a video. I have another. Oh, here we go. Hopefully you can see this okay. Because we talked about boiling point or melting point, vapor pressures, viscosity, surface tension. They're all related to the intermolecular forces. So the stronger those intermolecular forces, and we just talked about them, the stronger they are, the higher the boiling point, the higher the vapor pressure. Vapor pressure just means how much of it is evaporating. So if I put water on the table, a puddle of water and a puddle of like a alcohol, water has hydrogen bonding and alcohol just has dipole bonding. The dipole bonding, the alcohol is going to evaporate faster. Its vapor pressure is lower. Its bonding is not as strong as water. Water is going to take longer to evaporate. And we talk about vapor pressure because of, if you're doing remember the partial pressures, the vapor pressure of water, you have to subtract the vapor pressure of water from the barometric pressure to get the vapor pressure of a gas. We're bubbling butane up through the water into a graduated cylinder. That's an example of that. Viscosity is resistance to flow. So the stronger the intermolecular forces, the higher the viscosity because it resists flow because there is stronger bonds. Surface tension. It's kind of interesting. The surface tension, the stronger the bonds, then the greater the surface tension, which is again why water has such a high surface tension. You can see some of that over here. I hope you can see it over here. So was there another one? I think that was all of them. So I'm hoping that that's answering the question because I know that we had that as a question, intermolecular forces, as they relate to each of those. But please let me know if that's not. And I know the test is tomorrow. And I'm sorry this is coming out so late. Hopefully this helps. Good luck.